In this video we're going to consider the following problem. Let's say we've got two composable linear maps S and T. So what I mean by that is you have a linear map S from U to V and a linear map T from V to W, like this. So let's also suppose that we choose some bases, B for U, C for V, and D for W. It turns out that T composed with S is a linear map, so we could ask for the matrix of T composed with S with respect to the initial basis B and the final basis D. And we could also think about the matrices of T with respect to the initial basis C and the final basis D, and the matrix of S with respect to the initial basis B and the final basis C. There should be some kind of relationship between these three matrices, and in this video we're going to figure out what that relationship is. So here's the statement of the theorem. We have the same situation as on the previous slide. S is a linear map from U to V, and T is a linear map from V to W. And we let B be a basis of U, C be a basis of V, and D be a basis of W, with the notation that I've fixed here. Then what the theorem claims is that the matrix of T composed with S with respect to the initial basis B and final basis D is equal to the matrix product of the matrix of T with respect to the initial basis C and final basis D, and the matrix of S with respect to initial basis B and final basis C. We're going to give a proof of that, but before we give the proof we'll fix some notation. So we will write little lowercase t subscript ij for the ij entry of the matrix of T with respect to the initial basis C and final basis D. And what that means is that if you do T to the jth basis element from C, then that is equal to the sum from I equals 1 to n of T subscript ij times Di. Equally, we will write Sij for the ij entry of the matrix of S with respect to initial basis B and final basis C, and what that means is that if you do S to the basis element B subscript j, then that is the sum from I equals 1 to m of Sij times Cj. Having fixed that notation, let's go and do the proof. So what we will do is compute for any I and j the ij entry of the matrix of T composed with S with respect to initial basis B and final basis D, and we're going to see that what you get is the same as the ij entry of the matrix product of the matrix of T with respect to initial basis C and final basis D, and S with respect to initial basis B and final basis C. To figure out this ij entry of the matrix of T composed with S, what we're going to do is work out T composed with S at the jth basis element from the basis B. So to evaluate that, well, we use the fact that T composed with S of Bj is T of S of B subscript j, and we have an expression for S of Bj using the notation that we introduced for the matrix of S with respect to initial basis B and final basis C. So we can replace S of Bj by T of the sum from k equals 1 to m of Skj Ck. Now I'm using a different dummy variable here as I did on the previous slide, but it doesn't make any difference whether it's Skj Ck, the sum over k, or whether you use any other variable in place of k. It's simply a dummy variable, so it doesn't make any difference. So because T is a linear map, we can move it through this summation, and it's actually equal to the sum from k equals 1 to m of Skj times T of Ck. Now we're ready to use our notation for the elements of the matrix of T with respect to initial basis C and final basis D. We can replace T of Ck by the sum from I equals 1 to n of Tik Di. So if we move this Skj through the sum, then we get this expression here. And if we collect together the coefficients of Di, then what we get is this final thing here. So this is the coefficient of Di, the sum from k equals 1 to m of Tik Skj. But of course you'll recognise that from when we learned about a formula for the product of two matrices. So what is there in the brackets is exactly the ij entry of the matrix product of the matrix of T with respect to initial basis C, final basis D, and the matrix of S with respect to initial basis B and final basis C. Now the ij entry of the matrix of T composed with S with respect to initial basis B and final basis D is the coefficient of Di in this expression, and we've just seen that that is exactly the ij entry of the matrix product of the matrix of T with respect to initial basis C and final basis D, and the matrix of S with respect to initial basis B and final basis C. So we've completed our proof of this composition theorem. Let's see some useful things that we can get out of this composition theorem. In particular, we're going to be able to see how to answer the problem which I mentioned at the end of the previous lecture. So first of all, let's look what happens when you've got an invertible linear map T from U to V. It so happens that if T from U to V is invertible, then its inverse is also linear. We'll see why that is in a future lecture. But for now, let's just take that for granted. We'll fix a basis B for the domain of U and C for the codomain, B for the domain of T and C for the codomain of T. And then we're going to use the composition theorem. So think about the matrix of T with respect to initial basis B and final basis C multiplied by the matrix of T inverse with respect to initial basis C and final basis B. The composition theorem tells us that, you can imagine the B's kind of cancelling out. That's how I try to remember this stuff. So if you apply the composition theorem here, what you get is that matrix product is equal to the matrix of T composed with T inverse with respect to initial and final bases C. But T composed with T inverse is the identity on V. So what we've got is the matrix of the identity with respect to the same initial and final bases, and as we've seen before, that is the identity matrix. So here N is the common dimension of U and V. In particular, this product of matrices is equal to the identity, and so each one is the inverse of the other. So multiplying on the left by the inverse for the matrix of T, we get by the matrix of T inverse with respect to initial basis C and final basis B is the inverse of the matrix of T with respect to initial basis B and final basis C. Now in particular, if you take U to be equal to V, and if you take T to be the identity map, so the identity map is of course its own inverse, then what this would say is the matrix of the identity with respect to initial basis B and final basis C is the inverse of the matrix of the identity with respect to initial basis C and final basis B. So the problem we looked at the end of the last video was that if we knew the matrix of the identity with respect to some initial basis and the final basis E, how could we work out the matrix with the bases the other way round? And what this is telling us is that the first one is the inverse of the second one, and the second one is the inverse of the first one.